Okay, so I'd like to thank everyone for coming. This is quite an amazing gathering. When we first started organizing, we knew a lot of people would be coming. It makes sense because Peter Sarnak has had close to 60 PhD students, if you include his current students. Not to mention many postdocs and other students that he has mentored and supervised over the years. So it is not surprising, though overwhelming, that 300 people have registered for this conference. And so one thing I'd like to say is that an important message that Peter has imparted to us through his research and through his teaching is that mathematics should be viewed as a whole. And thus, while a unifying theme in Peter's mathematical output has been eigenvalues and zeros, he has connected with many areas in a way that always feels natural. The breadth and quality of Peter's mathematical output is reflected in the fantastic lineup of speakers that we have. And it is fitting that this gathering should take place on Peter's 61st birthday, a prime number. Not only is Peter at his prime, but we look forward to at least another 61 years of great mathematics and friendship. I'd like to ask everyone to join me in congratulating Peter on having been awarded the Wolf Prize this year. And I'd like to keep this short. And before I turn things over to Manjul, I'd like to thank a number of people who helped with this conference. First, we'd like to thank the awesome staff here at Princeton University and the IAS, especially Scott Kenny and Mary Jane. Second, I'd like to thank all our generous sponsors in alphabetical order. AIM, the Clay Math Institute, the Fields Institute, the IAS, the NSF, the Number Theory Foundation, and Princeton University. For those of you who are not familiar with the town in terms of food options, there's nearby there are a couple of university possibilities. There's a food court. Just up the hill to the left a bit, there's the CJL, which is another option right above the math department. If you go further up the hill, you'll hit Nassau Street. There's some restaurants on Nassau Street. You can go down Witherspoon Street, more options there, so you can just explore the nooks and crannies of the town. And I guess that's all I'd like to say. I don't want to take up time from the speakers, so without further delay, I'd like to hand things over to Manjul, who is going to speak to us on the average rank of elliptic curves, data conjectures, and theorems.
Okay, well, thanks very much. Can everyone hear me okay? No? Yeah? Okay. Well, thanks very much. It's a great privilege to speak here at this conference in honor of Peter's birthday. It's been a real pleasure and an amazing experience to have had Peter as a teacher and a colleague and a friend for all these past many years, and I look forward to many more years of that. Peter's had a tremendous influence on me ever since I was a graduate student. Since I came here as a graduate student, I came from a certain Ivy League institution near Boston as an undergraduate. And I came here interested in number theory, and well, given where I came from, in algebraic number theory. And I worked with Conway in my first year, and then my official PhD advisor was Wiles, because I knew I wanted to do algebraic number theory. But very quickly, I met Peter, and Peter was very generous with his time. He was ready to convert me into more analytic things immediately. which he did, despite having 12 other official PhD students of his own. He always made time for numerous other people to mentor, and I've certainly been one of them. So he was very generous with his time, despite having 12 PhD students and several postdocs. And then officially, he had me and many others. And as everyone knows who's talked to Peter, it's not very easy to get words in. But
Keep it quiet. I'm told by my mom to keep quiet.
That's right. So it was very hard to get words in, but anytime you went to his office, you always learned a ton. And I certainly learned a lot talking to Peter. I've also gotten better at getting some words in. The idea for the new Peter students is that you have to get to the beef very quickly, as he says. You have to get to the core of the matter very quickly, otherwise he'll feel that he has more interesting things to say, and it's usually true. So anyway, yeah, Peter's influenced me in many ways. What impresses me most about him, just as Mike said, is his global view of mathematics, the unity of mathematics, the global view. And that viewpoint, the way he sees mathematics and its interrelations from a really global standpoint and a unified standpoint is something that's really influenced me, and I know many people in this audience quite a lot. Peter's influenced me in many ways outside mathematics too. In addition to showing me how to use the combinatorial sieve in the right place, he's recommended a dentist. And he's advised me where to take a job. He advised Princeton. And I came to Princeton in large part because of him, of course. His influence on the department, the way his unified view of mathematics really unifies the department, makes it a very lively place to be. And so we're all very grateful in the department for what he's contributed to the Princeton atmosphere, making it one of the best places to work. So, okay, so maybe I could talk about Peter for the whole hour, but maybe I'll get to some mathematics. So actually, the story I want to tell today is something that originated in conversations with Peter and with Nick. One of the big influences for me when I came here that converted me into some analytic things was the work that Peter and Nick were doing together on their philosophy. And so some of the conversations that I had at that time with Peter and Nick is what started out the story that I'm going to talk about today. And what impressed me about the way they were approaching their work, well, first they were doing theoretical mathematics, but they were collecting a lot of data and using the data to formulate a philosophy, formulate conjectures. And then actually using those conjectures, using that philosophy to prove theorems that sort of gave evidence to that philosophy. And so that's where this title comes from. Data, conjectures, and theorems. All three are excellent guides to try and understand phenomena in mathematics. Okay, so the area that I want to talk about today is the average rank of elliptic curves, which, as I said, originates in conversations that I had with Peter and Nick when I was a graduate student. So the question is easy. The question is, if you range over elliptic curves over Q, what is the average rank of these elliptic curves? So to make this question more precise, we need a natural way of ordering the elliptic curves before we can talk about their average. So for example, if we ordered elliptic curves by rank, well, that wouldn't be very interesting if we're talking about the average rank. So we want to order them by an invariant that sort of measures the natural way in which we would order elliptic curves in a way that's not necessarily correlated to the rank, and then we want to treat rank as a random variable and understand how it's distributed. And well, the simplest notion of an invariant of an elliptic curve is that of the naive height, which is basically a measure of the size of the coefficients that define the elliptic curve. So more precisely, to define the height, you need the following fact, that any elliptic curve E over Q can be written as y squared equals x cubed plus ax plus b, where a and b are integers. And in fact, there's a unique such representation of any elliptic curve if you assume that for every prime p, you don't have the property that both p to the 4 divides a and p to the 6 divides b. Because if that happened, you could divide out a p to the 4 from a and a p to the 6 from b by a simple change of variable. And so every elliptic curve E over Q can be written uniquely as y squared equals x cubed plus ax plus b, where a and b are integers, and a and b have this minimality property at every prime. Okay, so this is a way of listing all elliptic curves over Q, just writing all y squared equals x cubed plus ax plus b, where a and b have this minimality property and are integral. Okay, so we have a canonical representation of every E over Q in this form. And so we can define the height by the size of these coefficients a and b that define this equation. And it's natural to compare the size of a cubed and b squared, because a is sort of like the G4, b is like the G6. So if E is EAB, y squared equals x cubed plus ax plus b, then we define the height of EAB as just the maximum, the absolute values of a cubed and b squared. And that gives a natural ordering on the set of these models of elliptic curves over Q. Okay, so that's what we'll call the height, the naive height. Of course, there are other invariants that one could use to order all elliptic curves. There's the notion of Faltings height, which is essentially the logarithm of the naive height. Another related measure of the size of EAB is called the discriminant, which is minus 4a cubed minus 27b squared. So conjecturally, that's about the same size as the naive height, if there aren't any conspiracies that cancel a cubes and b squareds. And finally, there's probably what's considered the most natural measure of size, called the conductor of E, which is a factor of the discriminant. So the point is that conjecturally, all these measures are expected to be about the same order of magnitude and give approximately the same ordering on all elliptic curves for all but a negligible proportion of elliptic curves. The advantage of the naive height, though, is that it's actually easy to write down exactly how many curves there are of naive height up to x. Whereas for discriminant and conductor, this is an unsolved problem. Conjecturally, it should be on the same order of magnitude, but provably, that's an open question. So if one could answer that question for conductor and discriminant, then a lot of the things I say today, you could ask for conductor and discriminant as well. But naive height makes it actually easy to talk about the set that you're averaging over. Okay, so we're going to order all elliptic curves by height. Okay? And we want to ask, what is the average size of the rank? If the average exists, otherwise we'll always be talking about the lim-inf and the lim-sup. And we want to know if we can bound where the lim-sup of the average rank, the lim-inf of the average rank lie. In particular, it would be nice to know that the lim-inf of the average rank is greater than 0. It would be nice to know that the lim-sup of the average rank is less than infinity. These were open questions only a couple of years ago. So the conjecture, of course, is that the average rank should be 1/2. So this conjecture goes back to Goldfeld in a paper he wrote about families of quadratic twists. But for general families, it was discussed in the work of Katz and Sarnak, where they predict that the average rank is 1/2. And more precisely, they expect that 50% of curves should have rank 0, and 50% of curves should have rank 1. So I won't get into their philosophy, how they got it, but maybe a quick explanation for why it should be 1/2 is that, well, you expect the root numbers of elliptic curves to sort of be equidistributed, 1/2 plus 1, 1/2 minus 1. And given those constraints, you sort of expect the rank to be as small as possible. And so for half the time, you expect rank 0 when the root number is plus 1, and half the time you expect rank 1 when the root number is minus 1. You don't expect any additional unexpected rational points to happen too often. So that's the philosophy, that the average rank should be 1/2, 50% rank 0, and 50% rank 1. However, previously this average was not even known to be finite, let alone 1/2. And it was not known to be more than 0, let alone 1/2. At least not unconditionally. And I'll say something about that in a second. I should also say computations don't give much support to the conjecture either. In fact, quite the opposite, as I'll show you. So the first computations that sort of indicated that this conjecture seems totally off were by Broomer and McGinnis in 1990. And what they showed is that as you went to higher and higher conductor, the proportion of rank 2 curves was actually increasing. We want it to be 0. And it's actually, the proportion of rank 2 curves was actually increasing, and up to where they got, it was already about 20% of curves were rank 2. And these computations were continued by Bekhtemirov, Stein, and Watkins in their huge computations. And they observed the same phenomenon. The proportion of rank 2 curves were increasing, the average rank was increasing. And here's a graph from their computations. So this is a graph of the rank of all curves of conductor up to 10 to the 8. It's a graph of the average rank up to conductor x, as x goes up to 10 to the 8. And as you can see, the graph starts above a half. And then it's only increasing from there. And it's totally unclear from this graph whether it's just increasing forever or whether it's approaching an asymptote. Certainly doesn't look like it's approaching a half. So this is a graph that I saw when I was a graduate student. And of course, I went to Peter right away and I said, how can you believe your conjecture given this data? It's one of my favorite stories from graduate school. And he looks at the data and he looks at the graph and he's like, well, the graph will turn around and approach a half. In his usual Peter type way. I showed it to Nick as well, and Nick had a similar reaction. So they had a lot of confidence in their conjecture. I was very skeptical. Okay, well that's so you can see it sort of looks like it may be approaching an asymptote, maybe around 1, or maybe it's just increasing forever. It's not clear whether, the graph, if you believe the data, it's not even clear that the average rank is bounded, because the proportion of rank 2 curves and the average rank is just going higher and higher. Well, the first theoretical evidence that the average rank should be bounded is due to Brumer, based on ideas of Goldfeld. So what Brumer showed in '92 is that if you assume the Riemann hypothesis for elliptic curve L functions, then the average analytic rank is bounded. And so in particular, if you believe the Boltzmann-Dyer conjecture, then the average rank should be bounded. If you believe also the Riemann hypothesis, then the average rank should be bounded. In fact, so assuming this generalized Riemann hypothesis and the Boltzmann-Dyer conjecture, Brumer showed that the average rank must be bounded by 2.3. And in 2004, this was improved a little bit by Heath Brown. So still assuming Riemann hypothesis and the Boltzmann-Dyer conjecture, Heath Brown improved this to average rank less than or equal to 2. And then a real breakthrough came in 2009 when Young further improved this to average rank, still assuming GRH and BSD, the average rank is at most 1.79. And this was very encouraging because, well, to get the average rank to strictly less than 2 means that a positive proportion of elliptic curves must have rank 0 or 1. Remember, we're conjecturing that 100% do, but at least this shows, assuming GRH and BSD, that a positive proportion must have rank 0 or 1. Anyway, so this was very encouraging. This at least showed that the average rank is bounded. And if the average rank's bounded, then maybe, well, assuming these conjectures, then maybe one can show it without assuming these conjectures. And, well, this was a very tantalizing problem for me because, well, there's this philosophy that leads you to believe that the average rank is a half, and that you look at the data and it's completely in contradiction to that. It's a very tantalizing. So the conjectures are very beautiful and very reasonable, and yet the data doesn't support it. And that made it a very exciting thing to try and get to the bottom of. And this theoretical evidence that it should be bounded meant that maybe some algebraic techniques inserted into the problem may lead to a solution. So what I want to talk about today is an unconditional proof of the boundedness of average rank. So this is joint work with Ariel Schenker, and we obtained an unconditional proof of the boundedness of average rank by working not directly with the rank, but with working with a related algebraic object called the n-Selmer group. So all we need to know here about the n-Selmer group, so I'll just say the n-Selmer group, Sn of E, of an elliptic curve, is a certain n-torsion abelian group, finite group, that fits into an exact sequence. So you can think of Sn of E as sort of being a product of the group of rational points modulo n times the group of rational points with the n-torsion of this mysterious finite group called the Tate-Schaff-Rabich group. So of course, the n-torsion in an elliptic curve tends to be trivial, and so this term E of q mod n E of q, right, if the group of rational points looks like z to the r, E of q mod n E of q just looks like z mod n to the r. Okay? So this n-Selmer group is basically some group that contains z mod nz to the rank times this mysterious n torsion in the Tate-Schaff-Ravitch group. So in particular, if the n torsion subgroup of E of q is trivial, which it usually is, what we're saying is that if you take n and raise it to the rank, right, that's the size of z mod n to the r, that has to be less than the size of this n-Selmer group of the elliptic curve. So n to the rank of E is at most the size of the n-Selmer group of E. That's all we ever need to use. And thus, to prove the boundedness of average rank, it suffices to bound the average size of the n-Selmer group for any n bigger than 1. Because that will mean that we have bounded the average size of n to the rank, and therefore the average rank can't be infinite. Right. Okay, so we work with this object called the n-Selmer group, and it suffices to know that the average size of the n-Selmer group is bounded to show that the average rank is bounded. Okay, and so here's the main theorem that we prove about the n-Selmer group. So this joint work with Arel Schenker. Let n be n most 5, 1, 2, 3, 4, 5. Then we show that when elliptic curves E over Q are ordered by naive height, the average size of the n-Selmer group is sigma of n, the sum of the divisors of n. So that's the result for n equals 1, 2, 3, 4, 5, is that the average size of the n-Selmer group is sigma n. And so in particular, the average size of the n-Selmer group is bounded, and so the average rank has to be bounded. And I'll say more about what bounds one gets by using these average sizes of the n-Selmer group a little later. I want to talk a little bit about the outline of the proof of how one shows that the average size of the n-Selmer group is this finite number sigma of n. So the outline is as follows. So there's sort of 3 steps. The first step is for each n less than or equal to 5, we construct a representation V of an algebraic group G, both defined over Z. So the representation is defined over Z, with the following property, that the orbits of the representation contain the image of the n-Selmer group in a natural way. So more precisely, so first of all, we want that the action of G on V over the algebraic closure has a free ring of invariance. And we want it to be generated by 2 elements, which we'll call A and B. And then we want this property that there should be an injective map from the n-Selmer group of EAB, right? Y squared equals x cubed plus ax plus b. We want the n-Selmer group of that elliptic curve with invariance A and B to map into the orbits of V of Z modulo G of Z, having invariance A and B. Okay, so this map injects the n-Selmer elements of an elliptic curve into orbits, integer orbits of this representation, and moreover, it preserves the invariance. The A and B of the elliptic curve agree with the A and B polynomial invariance of the representation. Then it's a theorem of Borel and Harish-Chandra that the number of orbits having a fixed A and B, number of integral orbits having a fixed values for the invariance is always a finite number. And so this in particular proves that the n-Selmer, if we find such a representation, this in particular proves that the n-Selmer group is finite in a different way. So it would give in particular a different proof of the Mordell-Weil theorem, or the Mordell's theorem, at least in this case. Okay, so we want to map from the n-Selmer group into the orbits where the invariants are preserved. And once one has such a representation, then one can try to then count the elements of this representation having bounded invariance A and B. Because if we do that, that would then be an upper bound on the number of elements in the n-Selmer groups of EAB where A and B are bounded. Okay, so we can try to then count. So we've changed the problem of counting n-Selmer elements into a problem of counting integral orbits for a representation over Z having bounded invariance. And once one counts the total number of orbits having bounded invariance, the last thing one needs to do is to perform a sieve, so that we obtain only the count of elements in the image of our map from n-Selmer elements into the orbits. And it turns out, well, since the definition of the Selmer group is defined by local conditions, it turns out that the elements in the image of this map star from the n-Selmer group to the integral orbits are defined by an infinite set of congruence conditions on the entries of V of z. And so one has to impose these infinitely many congruence conditions, which is a non-trivial sieving task. And once one does that, then one will get a total count of the number of n-Selmer elements of all EAB having bounded invariants A and B. And dividing by the number of elliptic curves will then give the average size of the n-Selmer group. Okay, so I want to say a little bit more about each of these steps. First of all, how does one construct these representations? Then how does one actually do these counts of integral orbits of bounded invariants? And then how does one do the sieve? I want to say a little bit about that. Okay, so first of all, how does one construct these representations? So the representations we use to parameterize n-Selmer group elements of elliptic curves are in the following table. So for example, n equals 2, the representation is of PGL2 acting on binary quartic forms. And the fact that such a map exists from two Selmer elements into integral orbits of PGL2 on binary quartics is actually due to Birch and Swinnerton-Dyer. So when Birch and Swinnerton-Dyer were doing their original computations leading to their conjecture, they were doing lots of rank computations. And they were doing it on a computer that has 4K of memory. And so the usual descent methods where you have to work over a number field and all this kind of stuff would not fit on a 4K computer. So they needed a way of computing ranks that didn't require much storage. Binary quartic forms have only 5 coefficients, and they're integer coefficients. So to store two Selmer elements of elliptic curves, instead of storing them as cohomology classes where you have to work over a number field, they store them as a quintuple of 5 integers, namely the coefficients of the binary quartic form. And so they developed this map of two Selmer elements into the integral orbits on binary quartic forms in order to do efficient rank computations. And in fact, it's the most efficient way of doing rank computations even today. This is what's used on all computer packages. It's called MW rank. It's been developed by John Cremona. But the original implementation goes back to Birch and Swinnerton-Dyer. And so they not only proved that there's a rational correspondence between the orbits and two Selmer elements, but they in fact showed that they're always integral representatives with the right invariants that represent a two Selmer element. For n equals 3, so people have since extended Birch-Swinnerton-Dyer results to higher values of n, in particular PGL3 acting on ternary cubics, parameterizes 3 Selmer elements, and then these other representations, pairs of quadratics, and then quintuples of 5 by 5 skew-symmetric matrices, they parameterize 4 and 5 Selmer elements respectively. And their integral theory has been developed by Castles and Cremona, Fisher, and Stoll in the cases n equals 3 and n equals 4. And then for n equals 5, well, this, in some sense, the result is classical, at least over the rational numbers, due to Cayley and Sylvester. But in more modern terms, it was worked out by Buchsbaum and Eisenbud. And then the integral theory was worked out by Fisher. So in some sense, this work was almost ready for us. We had to make a few changes just to get the groups correct, the group actions correct, so that the stabilizers gave the correct algebraic objects that were functorial. Okay, so how are these parameterizations obtained? So to really work with this, one has to understand the geometry of these representations. So let me just say, geometrically, an element of the n-Selmer group of EAB can be viewed as a map from a genus 1 curve C to Pn minus 1. That's the way of viewing an n-Selmer element of an elliptic curve EAB, is that it's a twist of EAB, a genus 1 curve C, whose Jacobian is EAB, and a map of it to Pn minus 1, embedded by a complete linear system of degree n. And furthermore, C has the property that it has points everywhere locally. That's what makes it a Selmer element instead of just a cohomology class. Okay, so basically we're thinking of n-Selmer elements as embeddings of genus 1 curves into Pn minus 1. And that's what an n-Selmer element is. And so if you take a genus 1 curve and map it, so say let's take n equals 2. If you take a genus 1 curve and map it to Pn minus 1, you're mapping a genus 1 curve to P1. When you map a genus 1 curve to P1, by Riemann-Hurwitz, it's going to ramify at 4 points of the projective line. And if you have 4 points on the projective line, there's a binary quartic form that has those 4 points as its roots. And that's where binary quartic forms come from for the two Selmer element. Similarly, if you take a genus 1 curve and map it to P2, That's a plane cubic. So in other words, a ternary cubic form. And the ambient automorphisms with P2 are PGL3, and that's what leads to the n equals 3 representation, PGL3 acting on ternary cubic forms. For n equals 4, you have pairs of quadrics in P3. If you take a pair of quadrics in P3, it turns out it intersects in a genus 1 curve. And conversely, if you have a genus 1 curve in P3, it's always the complete intersection of two quadrics. And so that's why the representation for n equals 4 is pairs of quadrics, right? 2 tensor sim 2, 4. And the ambient automorphisms are a certain natural subquotient of GL2 cross GL4. Okay, so those are all classical. And it seems like when you're looking at these three constructions, it looks like, well, things have to stop there. Because when you look at a genus 1 curve in P4, it turns out that's not a complete intersection of anything. And so how are you going to parameterize it by forms? And yet, classically, it was known that you could parameterize genus 1 curves in P4. And here's how you do it. You take 5 tensor sim 2, 5. So you take 5 copies of, oh, sorry, that should be wedge 2, 5. I should write this in. So in other words, 5 skew-symmetric 5 by 5 matrices. I put a sim there as a typo. So this is sort of, you can think of it as 5 skew-symmetric matrices. And so how can you use a quintuple of 5 by 5 skew-symmetric matrices to get a genus 1 curve in P4? Well, what you can do is you can view this. You can make this a 5 by 5 skew-symmetric matrix of linear forms. Let's see. So you get, by just multiplying each one by a variable and summing it up, you get a 5 by 5 skew-symmetric matrix of linear forms. Okay? And then you can take its determinant. And what happens when you take the determinant? Well, you get 0. Right, because it's a skew-symmetric odd-dimensional matrix. Okay, so if you take the determinant of this thing, it's going to be 0 because it's an odd-dimensional skew-symmetric matrix. So instead, what you can do is you can take its 4 by 4 principal Pfaffians, right, determinants, square roots of determinants. And if you take those 4 by 4 principal minors, well, the determinants will be squares, right, because it's a skew-symmetric matrix. And so the determinants are degree 4 forms in 5 variables, so the square root is a degree 2 form in 5 variables. And so you get an intersection, you get 5 quadrics this way. And it turns out if you intersect those 5 quadrics, you get a genus 1 curve in P4. And conversely, if you have a genus 1 curve in P4, it always is the intersection of 5 quadrics, not a complete intersection, but an intersection of 5 quadrics. The point here is that not every 5 quadrics intersect in a genus 1 curve. Usually 5 quadrics in P4 will intersect to nothing. But there are some special sets of 5 quadrics that intersect in a genus 1 curve, and it's exactly those that can come from a quintuple of 5 by 5 skew-symmetric forms. And so this is actually a classical construction that goes back to Cayley and Sylvester, but thinking in terms of modern genus 1 curves and cohomology classes in E5, this was worked out by Buchsbaum and Eisenbud and Fischer. But it really shows that, but these are all classical constructions. And so here's a remark. If we knew a way of describing maps C to Pn-1 for n bigger than 5, then a lot of what our methods do would allow us to understand n-Selmer for n bigger than 5. So we need a way of parameterizing genus 1 curves in Pn-1 for general n. And they don't always have to be complete intersections, as this case shows. And it's an interesting algebraic geometry problem that really hasn't been worked on since the 19th century, in some sense. Already for n equals 5, the invariants were so large, it's kind of a miracle that people at that time worked out the invariants and worked out this theory. But it's time for people to think about it again, and I think that's a nice algebraic geometry problem. Okay, so these are the answers and the parameterizations for n equals 2, 3, 4, and 5. And what's amazing is that this is not just a rational theory over a field, but in fact works over the integers. Okay, so those are our representations. And so we have maps from from n-Selmer groups into these integral orbits where the invariants are preserved. And so we next wish to count the total number of elements, total number of integral orbits that have bounded A and B, having height less than x. So the way to do this, what we do is we first construct a fundamental set. Well, what we're eventually going to do is we're going to make a fundamental domain for the action of g of z on V of r, the real vector space. And we're going to count the number of lattice points in there that have bounded A and B. That's equivalent to counting, if you count points in a fundamental domain, that's equivalent to counting orbits. Okay, so how do we make a fundamental domain for the action of g of z on V of r? So first what we do is we construct a fundamental set L for the action of g of r on V of r that's absolutely bounded in V of r. Okay, so it's not totally obvious that you can do this, but we're going to take the real group and make it act on the real vector space, and we want to construct a fundamental set that's absolutely bounded. And it turns out we have a general way of constructing sets bounded, absolutely bounded fundamental sets for the real group acting on the real vector space. When we're restricting to bounded invariants. Okay, and then second, we construct a fundamental domain F for the action of g of z on g of r. So a fundamental domain in the group for the action of the integral group on the real group. And this can be done in the way that Borel and Harshchandra describe in their paper. You can assume that it's contained in a Siegel set. So in other words, you can write F as n prime a prime k. This is a subset of the Iwasawa decomposition. People usually write K-A-N, but I like N-A-K because it's the last letters of Peter's name. So here, so n prime, a prime, and k are subsets of n, a, and k. So n prime, so in the fundamental domain, n prime can be taken actually to be a bounded set of lower triangular matrices. So n prime is bounded. A prime is the unbounded part of this fundamental domain. And then k is the maximal compact subgroup of G of R. It wasn't just because of Peter's name. It's actually more convenient to do this. Okay. Okay, so the point here is that we've made a fundamental domain for the action of the integral group on the real group so that all the non-compact part of it is contained in A prime and contained in the torus. Okay. And so since we now have a fundamental domain for G of R on V of R, and then we have a fundamental domain for G of Z on G of R, if we multiply those, that gives a fundamental domain for the action of G of Z on V of R. So if we take F times L, right, so the F constructed in B and multiplied by the L constructed in A, then that gives a fundamental domain for the action of G of Z on V of R. Right, the reason being that V of R mod G of Z is the same thing as V of R mod G of R times G of R mod G of Z. Right, the G of R's cancel. Okay. And in fact, more generally, if you, instead of just taking F times L, you could take F times G times L, where G is any element of G of R. That's still going to preserve the fact that it's a fundamental domain for the action of G of Z on V of R. So we've constructed all these fundamental domains, namely F times G times L, where G can be any element of G of R. Right, because if you translate a fundamental domain, you still have a fundamental domain. And thus, we wish to count the number of integral points in this fundamental domain we've constructed, FGL, having height less than x. That's going to be the total count of orbits having height less than x. The problem is that this region, FGL, if you cut it off, even if you cut it off with the condition that the height is less than x, it has finite volume, but it's unbounded. So it's this finite volume but unbounded region in Rn. It has these cusps going off to infinity, which Peter taught me are called tentacles in the lingo. And we want to know the number of lattice points in this region that has these tentacles going off to infinity. So it has it's finite volume, but it has these tentacles going off to infinity, which may have lots of integral points in them. In fact, they do. So this is in general a difficult problem. If you have this is a problem in the geometry of numbers where you're trying to count the number of lattice points in some region, but that region is not bounded, but it has tentacles going off to infinity. So the general philosophy is that when you have a nice round-looking region, the number of lattice points in a region should be approximately the volume. But when the region is unbounded and has tentacles going off to infinity, then that philosophy doesn't necessarily hold. You could have a tentacle that has lots and lots of integral points and a very tiny volume. Or you could have a tentacle that has a very large volume but no integral points. Both of those things can happen. And in general, well, it's a difficult problem to sort that out, but especially in the spaces that we're talking about, because some of these spaces are 50-dimensional, and the height is a degree 60 function, and the number of tentacles is about 1,000. So this, in general, can be a very difficult problem. But what we do is we take advantage of the fact that the number of points in this region, FGL, is independent of G, because they're all fundamental domains. And all fundamental domains have the same number of lattice points. Even though they sit differently in the space, they all must have the same number of lattice points because they are all fundamental domains. And so since we have many such fundamental domains, FGL, what we can do is we can take an average over a compact continuum of them. And this, in effect, so we have this fundamental domain. We take G to be in a small ball, and we translate this fundamental domain by the small ball. And what that ends up doing is thickening the cusps so that we can count in them better, and then we divide by the total number of fundamental domains that we were using. So this is the common idea in analytic number theory. It's kind of a smoothing idea, an averaging idea. And so let me say a little bit about how it works out in this case. One has to then use some geometric and algebraic ingredients to then handle these thickened cusps. Okay, so here's how it goes. So let nvx be the number of generic g of z orbits on v of z having height less than x. So here generic, and this turns out to be a key notion, the notion of generic means that the corresponding map from C to Pn minus 1 doesn't come from a map of C to a smaller Pn. In terms of n-Selmer elements, generic means that the corresponding map C to Pn minus 1 doesn't correspond to an n-Selmer element of order less than n. Okay, generic means that we're actually talking about order n n-Selmer elements in this n-Selmer group. Okay, and I'll say why generic turns out to be important in a second. But when we count generic points in the fundamental domain, it turns out to be easier after one does this averaging method. Okay, so let me explain. So let G0 be some small ball sitting inside G of R. Okay, and we're going to look at these fundamental domains F, G, L, where G ranges inside the small ball G0. Okay. So G0 is the closure of some bounded open set in G of R. And we're going to let this little g range in G0 and count points in FGL. Okay, so here's a essentially tautological statement once you understand what it's saying. So nvx, the total number of orbits of g of z on v of z having height less than x, is going to be an integral over g and G0 of a certain constant function divided by that same integral. Okay. And that constant function is the number of vectors v in FGL, this fundamental domain, that are integral and generic, where the height is less than x. So that quantity inside the integral is independent of g. So I can integrate it over all g and G0 and then divide by the integral of g and G0. Okay. So I've just taken the same count, I've integrated it, and then divided by what I'm integrating over. Okay, so this is just the fact that all fundamental domains have the same number of points. And now, the point is that we can interchange the order of integration. Remember, we're counting points v in FGL, where g is fixed. We can now let g vary and fix the element of f. So we can integrate over, instead, we can integrate over f and replace the little g by G0. So that's what I've done there. So instead of counting v in FGL, we're going to count v in h G0L, right? Where now h is ranging over f. So that's just a sort of changing what we're integrating over. Is that clear? Okay, so why is this an improvement? Well, in the first case, we were counting points v in FGL. And FGL was this region that has these cusps going off to infinity and is difficult to handle by geometry of numbers. But now, when we're integrating over f instead, and fixing G0, we're now counting points in H, G0L. Remember, G0 we chose to be compact, L we had chosen to be absolutely bounded, and H is fixed. So this region now, H, G0L, is now a compact region, where we can apply more standard geometry of numbers arguments. Okay, but the reason this is still subtle is that h, right, when we're counting points in h, g0, l, h is ranging through f, and f is this non-compact set. So as h goes into the cusps of this fundamental domain f, this region h, g0, l becomes very skew. And that's when the geometry of numbers methods, don't apply as well. Well, I mean, they don't apply at all because the region is so thin that the number of lattice points inside can be very unpredictable. But what we show in those cases, when h goes very far into the cusp of f, then it turns out that most lattice points inside h, g naught l, you can show by algebraic methods, have to be non-generic. That some kind of degeneracy happens. So there are lots of points. So what this is showing is that there are actually lots of points in this cusp inside Euclidean space. But because there are lots of lattice points, you might expect that there's some algebraic reason. There's some algebraic variety on which there are lots of lattice points. And that algebraic variety corresponds to non-genericness. And so the goal is to show that so what we do is we break up this partition F into a main body and a cuspidal region, depending on A prime, which was the unbounded part of the torus inside the fundamental domain. And when F is sort of in the main body, the region H, G naught L is fairly round, and we can get a very good estimate for the number of lattice points using the geometry of numbers. When H goes far off into the cusp, then this region becomes very thin, and we try to find algebraic varieties in there that contain most of the lattice points and show that those algebraic varieties correspond to the n-Selmer element having order strictly less than n. For some of the larger cases, like n equals 5, this involves breaking things up into about 1,000 pieces. And in each case, there's a different subvariety that forces you to be either non-generic. And sometimes when you can't find those subvarieties, then you have to show by hand that the number of lattice points is negligible for each case. But the method has become fairly systematic now. And so in the end, what that ends up proving, since in the cusp we're saying that there aren't that many points that you care about, in other words, there are not many generic points in the cusps, this all allows finally one to show that the number of orbits number of generic orbits having bounded invariance, h less than x, is just the volume of that fundamental domain. So volume of FGL with the condition that the height is less than x.
And 5, 6 is for all cases?
For all cases, yeah. Because the number of elliptic curves, so this is the key point, right? The number of elliptic curves up to height x is x to the 5, 6. Because, right, a cubed is bounded by x, and b squared is bounded by x. So a goes up to x to the 1/3, b goes up to x to the half.
I didn't see the little...
Oh, I see. Right. So the total number of elliptic curves up to height less than x is x to the 1/3 times x to the half, which is x to the 5, 6. And the key point is that you get a volume which is on the order of x to the 5, 6, and then a lower order term. And that's why the average size of the n-Selmer group is bounded, because you divide something on the order of x to the 5, 6 divided by the total number of elliptic curves is x to the 5, 6. Okay, so the answer always turns out, for the total count of generic orbits of height less than x, the answer always comes out to be just the volume of the fundamental domain. And this fact would not be true if we were counting all lattice points. The number of lattice points blows up. But since we're only counting generic lattice points, so this...
This is identical to your counting number fields.
Yeah, very similar. Very similar to how counting number fields went. Except there are a lot more subvarieties that can cause non-genericness now. Right? Okay, so when counting only generic elements, you really just get the volume of the fundamental domain. Okay, so once we have that, the proof that the total number of orbits is the volume of the fundamental domain, we now just have to sieve to count those elements that are in the image of the n-Selmer group of our map. So this is actually the most technical part of the whole work. To carry out the sieve, one has to essentially determine the density of square-free values taken by the discriminant polynomial, minus 4a cubed minus 27b squared. And this is an irreducible polynomial in many, many variables. For example, in the case n equals 5, it's a polynomial of degree 60 in 50 variables, and we want to know the density of square-free values taken by this polynomial. Early on, we thought that was a totally impossible task. But it turns out one can handle this by developing sort of a new geometric sieve technique. So this is based on work of Ekadal, sometimes called the Ekadal sieve. also has its origins in a work of Peter that came before Ekadal. And so one can build on these works to prove a sieving lemma that turns out to be very useful in these kinds of questions. So here's the sieving lemma. Suppose you have some ball, a finite measure, okay, in Rn, and we want to count the number of points in this ball as it's homogeneously expanding. But we want to count the number of points that lie away from a certain codimension 2 subvariety. Defined over Z, we want to stay away modulo p for all large p. Okay, so let B be a region that's going to be homogeneously expanding. Let Y be any subvariety that has codimension, let's say at least 2, or you can do at least 1, but you don't get anything. Okay, and then R is going to be our expanding factor, and M is going to be the bound after which we're going to consider primes. Okay, so then here's a statement that if we look at the number of lattice points inside RB, okay, we've homogeneously expanded B, such that if you reduce mod P, you lie on this codimension 2 subvariety, the FP points of this codimension 2 subvariety for some large P. Okay, so we want to count the number of points in this homogeneously expanding region such that when you reduce it mod P, you're on this codimension 2 variety for some sufficiently large prime, modulo some sufficiently large prime. And we want to say that there are not so many such points. And that's what this estimate allows you to say, that the total number of points is R to the n, but the total number of points that reduce mod P onto this codimension 2 variety mod P is big O of R to the n divided by a positive power of m, once k is at least 2. Okay, so why is the closed subscheme of an defined over Z? And we want to count the number of points that reduce mod P onto this codimension 2 subscheme, mod P, for some P bigger than M. And when M is large, we're saying that the number of such points is negligible. Okay. And here the implied constant depends only on B and on the variety. So this theorem was proven based on work of Ekadal and Sarnak. We've just made it quantitative, so it can be used and inserted into a square-free sieve. And so once this theorem is proved, this takes care of sieving away those V that have square-full discriminant at P bigger than M for mod P reasons. So when you have a polynomial and you're trying to do a square-free sieve, sometimes that polynomial can be square-full at P for mod P reasons. So there's sort of two mod P conditions that force the discriminant to be a multiple of P squared. If there are two mod P conditions that force your discriminant to be a multiple of P squared, then you can apply this theorem, because those two mod P conditions define a codimension 2 subvariety. The hard part in any square-free sieve is when your polynomial is taking square-full values at P for a single mod P squared reason. And it's not, so then it's only lying on a codimension 1 variety, mod P. That's what's hard in all square-free sieves when you're trying to prove that polynomials take square-free values. So to handle those V that have square-full discriminant at P for mod P squared reasons, in these cases, what we can do is we can use the symmetry group G on V to transform that mod P squared condition into two mod P conditions. So amazingly, in all these representations, not just these four that I'm talking about here, but in all such sort of co-regular representations where you have a free ring of invariance, it turns out in all cases that we've found so far, this can always be done, that when you have a large enough symmetry group, you can transform mod P squared conditions into two mod P conditions and then apply this theorem. And so that's what allows us in these cases to show that these polynomials, these discriminant polynomials, take the correct densities of square-free values. Actually, in some cases, it doesn't work. The symmetry group is just not large enough to change every mod P squared condition that makes you squareful into two mod P conditions. In those cases, what we've always been able to do is map our representation into a bigger representation with a larger group of symmetries. And then using that larger group of symmetries, you break down the mod P squared condition into two mod P conditions, and then you can apply this algebraic geometry lemma. So it doesn't always work in a straightforward way. Sometimes the symmetry group is too small. So for example, PGL2 acting on binary quartic forms is too small. So we map it into a bigger space with a larger group of symmetries, break mod P squared conditions into a geometric condition mod P, that's codimension 2, and then we can apply this theorem. So in any case, in all cases, we've been able to determine the correct density of square-free values, and that allows us to sieve to the elements of V of Z mod G of Z lying in the Selmer group And so now to calculate the size of the Selmer group then, all that needs to be done now is first we need to compute the volume, and then we need to compute the local densities at every prime p, multiply that all together, and then divide by the total number of elliptic curves. And that's going to be the average size of the n-Selmer group. So to compute the volume, we use the following change of measure. The dv, the Euclidean measure on v, turns out to be, well, a certain Jacobian times dA, dB, dg. That's a change of measure. So right, you can remember we had this fundamental set L for the action of g of r on v of r. And then you can multiply that by any element of GRR, and you get the whole vector space. And it turns out that this dv, you can just write down as dA times dB, those two invariants, A and B. It's just dA times dB times the higher measure on the group, times a certain constant Jacobian. So this is kind of a remarkable thing, right? You think that when you do a change of variable, you might get some complicated function. But in fact, it's just it's actually an actual equality of measures. dv is actually equal to dA times dB times dg for general representations that have a free ring of invariance. And so, if we want to compute a Euclidean volume, we can just do an integral over A and B in the higher measure. And so this makes it all possible to do. So the expected number of order n elements, and this holds also over ZP. This is an algebraic identity, so it holds even over doing integrals over ZP. So the local densities can also be computed using this change of measure formula. So the expected number of order n elements in the n-Selmer group is, well, it's the real volume, which is going to be, well, J times the volume of the group over R modulo the group over Z, right? That's the fundamental domain for the group, times an integral over AB, where the height is less than x, times the total number of orbits, real orbits, which turns out to be E of R mod n E of R, divided by the stabilizer over R, which is the n torsion of the elliptic curve over R, and integral over all A and B. And then the local factors at each P are given similarly. But now we're going to apply this lemma over the p-adics. So we get the same Jacobian, but it's p-adic valuation, times the volume of the group over ZP, times an integral over all A and B in ZP, which is 1. Yeah. And then the number of orbits, which is E mod NE over QP, and then divided by the stabilizer, which is the n torsion elements of E of QP. And, well, if you look at this, well, by the product formula, the Jacobian doesn't matter. We didn't even need to compute what it was. And, oh yeah, we have to divide by the total number of elliptic curves, which is that integral. And so the product formula says that the J's cancel. And then if you look at these blue terms, it turns out that each of those two blue terms are constants just depending on the place. And there's another product formula that says that they all cancel when you multiply them all together. So basically everything cancels. And all that's left is this product of volumes. And for all these formulas, we're using what's called the Tamagawa measure on the group. And, well, if you take a Tamagawa measure on the group and you take this real volume and multiply it by all the p-adic volumes, what Tamagawa showed is that you get a Tamagawa number of the group. Everything cancels, and we obtain simply the Tamagawa number of the group, which, so for example, for PGL2, Tamagawa number of PGL2 is 2. In general, the Tamagawa number of PGLn is n, and that's where this n is coming from. And so the average number of order n elements in the n-Selmer group is n. That's the theorem. That's the right way of thinking about the theorem about average size of n-Selmer group, is that the number of order n elements in the n-Selmer group, the expected number is n. And so we've proven that when elliptic curves E over Q are ordered by height, the average number of order n elements in the n-Selmer group is n. And that's what leads to, if you sum over the divisors, to get all orders, then you get the average size of the n-Selmer group being the sum of the divisors of n. Okay, so that's how the proof goes of that theorem. Obviously, we're naturally led to the conjecture that the average size of the n-Selmer group should be sigma of n for all n. And we only prove that up to n equals 5 at this point. But it's natural to, for the reasons behind the proof, it's very natural to think that the average size of n-Selmer will always be sigma of n. So how does this conjecture, the sigma n conjecture, relate to the average rank conjecture of Goldfeld and Katz and Sarnak? Well, it turns out that, well, suppose this sigma n conjecture is true for all n. Then when all elliptic curves over Q are ordered by height, it implies the Goldfeld Katz and Sarnak conjecture that 100% of elliptic curves have rank 0 or 1. And if you further assume that root numbers are equidistributed, if you assume parity, then it implies that It's 50-50, rank 0 and rank 1. So this is a natural way of approaching the conjecture, is through showing that the average size of the n-Selmer group is sigma of n. And if we did this for all n, then we would actually obtain the conjecture, but we'd get it up to 5, and that's already significant enough to get good bounds on the average rank. So if you know it up to 5, what does it say? Well, it's enough to say that the average rank is bounded. And in fact, it's enough to say that the average rank is bounded by 0.885. In particular, it's bounded, average rank is less than 1. And so as a consequence, when elliptic curves E are ordered by height, positive proportion have to have rank 0, because the average rank is less than 1. And another consequence that comes out is that when elliptic curves are ordered by height, more than 80% have rank 0 or 1. So the conjecture is that 100% do, but this is already enough to show that more than 80% have to have rank at most 1. There's a question about what about lower bounds? So if we combine all these counting results with the recent work of Skinner, we can also now obtain a lower bound on average ranks. This is joint work with Skinner, where we show that a positive portion of elliptic curves actually have rank 1. So this is by inserting root number arguments together with Skinner's converse to Gross-Zagier and Kolyvagin. So in particular, the average rank of elliptic curves is strictly positive. So I'm really fond of this theorem because it uses everything in the arithmetic of elliptic curves that's basically ever been done. It has to throw everything at it. Gross-Zagier, Kolyvagin, the work of Skinner, Urbain, and Skinner, and all these counting techniques and root number methods all go into, and works of the Dachschitzers and Bertolini, Darmont, Prasanna, and basically everything that's ever needs to go into this to show that. So what this slide shows is that a positive proportion of elliptic curves have no rational points other than the point at infinity, and a positive proportion have infinitely many rational points. And we basically had to throw everything at it to get this. What about analytic rank? Well, the same work of Skinner and Urbain can be used to show that a positive portion of elliptic curves have analytic rank 0 now. And the aforementioned work with Skinner also allows us to now show that a positive portion have analytic rank 1. So in fact, a positive portion not just have rank 0 and rank 1, but also analytic rank 0 and analytic rank 1. And so a positive portion of elliptic curves satisfy the Birch and Swinnerton-Dyer conjecture, both with analytic rank 0 and with analytic rank 1. And a lot of, some of the work that we've been doing lately, this is work with Skinner and Zhang, so using Zhang's recent advances on Kolyvagin's work, we can now show, so we were wondering what percentage we can say here. So originally this percentage was very tiny, negligible, but also inserting work of Zhang, this proportion is now very sizable. Most curves, in fact, more than 66% we can show, have analytic rank 0 or 1. And so at least 66% of elliptic curves satisfy the Birch and Swinnerton-Dyer conjecture with analytic rank 0 or 1. Of course, the conjecture is that 100% do. And in fact, here's the second part of our theorem, is that if this sigma n conjecture is true, if the n-Selmer group has size sigma n for all n, or even any infinite sequence of n, then 100% of curves have to have analytic rank 0 or analytic rank 1. So the 66% we're getting is what we get because we've proven the conjecture up to n equals 5. And if we knew it for all n, then we'd know that 100% of curves have it, satisfy BSD and have analytic rank 0 or 1. Okay, so we know a positive portion of rank 0, analytic rank 0, analytic rank 1, rank 1. And all these results, as the sigma n conjecture holds, are going towards the Katz, Sarnak, Goldfeld conjecture, the average rank conjecture. I want to end by asking, well, what's the deal with the data then? That's the original reason why I got into this. So recall, we had this picture, and it looks like the average rank is approaching this asymptote. And Peter said this graph has to turn around. But everything we've proven until now doesn't actually prove that. Only if we knew sigma n for all n, it would prove that. But since we know sigma n up to n equals 5, we know the average rank is bounded by 0.885. That seems very suspicious. Maybe it's only true up to n equals 5, and maybe it is approaching an asymptote. So okay, something has to be resolved about this. Does the graph turn around? The graph is staying below 0.885, the proven upper bound on average rank. So it's totally consistent that the average rank just increases forever. The results don't yet prove that the graph turns around. Seems that one might have to compute much further to see the graph turn around, if it in fact does. However, to prove that it does eventually turn around, you don't actually have to see it turn around. You just have to compute far enough so that it passes the upper bound that we proved. Right? Because if we see that the average rank graph goes above 0.885, well then at least we know it has to turn around even though we don't see it. And so such a large computation, also recomputing everything with respect to height, because that's where the theorems apply, has recently been carried out, finishing just this weekend, by Balakrishnan, Ho, Kaplan, Spicer, Stein, and Wiegand. They used up their computer resources at their universities for the past many days. It's just finishing this weekend. They compute the rank of all curves of height less than 10 to the 8. Okay. So that's going quite far. And this is the result. So the initial part of the graph looks the same as the original Vectarmov, Stein, and Watkins data, but now they've gone far enough so that it's actually past the 0.885 mark, which is at the red dotted line. And so the graph has to turn around, even though we don't see it, even though we don't see this yet. Here's a graph with respect to the log height, so it's more dramatic. You can see that it's past the mark. And so that's the work with Shankar together with this work of Balakrishnan, Ho, Kaplan, Spicer, Stein, and Wiegand, and now proves that when elliptic curves are order of height, the average rank graph doesn't actually keep increasing, but it does turn around. And more precisely, to prove it does reach some maximum value, the average rank, that must be above 0.89. So anyway, I couldn't think of a better place to stop. This is a birthday present for Peter. Thanks for that comment, which led to a lot of wonderful mathematics. Happy birthday to Peter. Thank you.
Okay, thank you, Manjul, for a very nice talk. Does anyone in the audience have any comments or questions they'd like to make? We have time for a few brief ones.
Does the sigma-n conjecture tell you anything about the behavior of Shah?
Oh, it does. Yeah, so the sigma-n conjecture sort of tells you it tells you something about the average size of the n torsion in Shah. In fact, this is something that I would have talked about next if there's time, but we now have actually a much more general conjecture. That's joint work with Kane and Lenstra, Poonen, and Rains. That sort of generalizes the sigma-n conjecture. So what it does is it models the Selmer exact sequence. And we can model the entire Selmer exact sequence in a style modeled after Cohn and Lenstra and Poonen and Rains. And in fact gives exact distributions of Shah and of the Selmer group and of rank all at once. And so it actually gives a distribution on the set of Selmer exact sequences. And then when you specialize to Shah, it recovers the Cohen-Lenstra heuristics that developed by Delaunay for Shah. It recovers the Poonen-Rains heuristic for Selmer. And it recovers the Goldfeld, Katz, Sarnak heuristics for rank, all simultaneously. So there is a sort of unified conjecture that puts together Shah and Selmer and rank all in one conjecture. So I totally believe it all now. Yeah, I totally believe your original comment now.
Do you believe that the rank is bounded?
Oh, that's a different question. I used to think that the rank is unbounded. I've been changing my mind a little bit. I'm now agnostic.
Okay, we can maybe take one more question or comment, if there are any.
Yeah, I have one. Just so you know, I had a little more information than you might have thought. If you look at x cubed plus y cubed equals m, this excess rank was found by Kosmark and Zagier, and that turned around by, I think Watkins did computations, and it turned around quite fast. I mean, it was also around those numbers, but it turned around more dramatically. So
over function fields, though, right?
No, numerics.
Oh, okay.
And so there was a belief there was excess rank, but the turning around happened more dramatically. So
I see. That's what
it had to happen.
Yeah. I see. Very nice.
Yeah.
Okay, we need to move on to the next talk. So let's thank Manjul again. And